Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Welcome in this workshop. I'm going to give a talk about lattices and cryptography. So if you don't know what is lattice, I will give you all the tools for understanding this area. So the contents will be like this. First, I will say the definitions and properties of lattices, and then I will say some words about the famous algorithm in lattices called the LATTICE algorithm. Also, I will see some applications of this algorithm to RSA. To Andrew, to other crypto systems, mainly LV and GTH. And I will finish this talk by a short conclusion. So the first part of this talk will be about lattices. So lattice is simply something like Dorian. If you see the envelope of a Dorian, you can see that there are points, regular points in Dorian, and this is exactly the definition of lattice. So, from the mathematical point of view, lattice is a space, like a vector space. So you have two parameters n and d. Two positive integers, and if you have d vectors b1, b2, and so on till bd are vectors, and these vectors are linearly independent, then you can build lattice by generation vectors using the basis b1, the bd. And the lattice will be the set of all linear combination of the vectors of the lattice. So here the coefficients are integers, and you can find that this set have mainly properties like vector spaces. For example, if we take n equal 3 and the dimension equals 2, then b1 and b2, the vector b1 and vector b2 will give lattice, and this lattice is set, is the vectors b such that b is a linear combination of b1 and b2. Here x1 and x2 are integers. And we can draw such lattice. For example, here in this picture, we have b1, the vector b1 and the vector b2, and we can find that the lattice is the linear combination of b1 and b2, where the coefficients x1 and x2 are integers. So if you draw these vectors, you can find that we have b1 here, we have b2 here, and we can find, for example, b1 plus b2 will be here, and b1 plus double b2 will be here, and so on. So we are going to get only the points in this picture. So we can find, for example, this point using b1 and b2. But here in this place we can find a linear combination of b1 and b2 if we want only the coefficients. So this is the lattice which basis b1 and b2. And there are many properties, theorems and measures on lattices. For example, if you have a lattice and the basis you can find that you can describe this lattice with matrix. So the matrix is n times t, and all the numbers here in this matrix are numbers, and we can find that every vector in the lattice can be computed using this matrix. So every lattice is equivalent to is determined completely by a matrix. So if you have a lattice, you can find a matrix, and conversely, if you have a matrix, and if the vectors are linearly independent, you can find a lattice in this situation. Also, this proposition that says that a lattice have infinitely many bases. For example, if you have a lattice L with this lattice B1, B, Bt, and if you have another, you can find another basis B1 prime to Bt prime, and to get the new basis from the first one, you have to multiply the first one by a matrix U, and the determinant of U is plus or minus 1, and all the numbers in the matrix U are integers. So we can move from basis to another by using the matrix U, such that the determinant of the matrix is plus or minus 1. So we know that there are infinitely many solutions to this determinant, and this means that lattice has infinitely many bases. So we can find for the same lattice basis number 1, number 2, and so on, and we can get that some bases are better than others. So I will say later why basis is better than another, but for the moment we know that we can move from a basis to another using matrix U, such that determines U is plus or minus 1. And here definition, an important definition in lattice, it's about determinant of the lattice. So if you have the lattice L with the basis B1 with BB, then the determinant of the lattice, or also called the volume of the lattice, is simply the square root of this, of the determinant of the product of basis B, matrix B, by its by Bt, and Bt is simply the transposition of B. So we can find that Bt times B is a square matrix, and you can find the determinant, and you can compute the square root, and this square root is called the determinant of the lattice, or the volume of the lattice. And in this situation, we can find that since there are infinitely many bases for lattice, we can find that the determinant is independent of the basis. It means that you can get the determinant of the lattice using any basis for the lattice. Here is an example. If we take n equals 3 and the dimension is 2, then there is a basis for a lattice with B1. B1 is like this, B2 like this, and we can find that the matrix of the lattice is this matrix 1, 3, minus 2, 2, 1, and 0. And if you compute Bt, this will be the transplant of matrix B. and the product of BT times B will be this square matrix, and the determinant of this square matrix can be computed easily. And in this equation, you can find that the determinant of the lattice is simply the square root of this product, and it will be the square root of 69. So this is a very important definition for lattices, because we will use the determinant of lattice in many properties and theorems. So this proposition shows that the determinant of a matrix for lattice is independent of the choice of the lattice. So the proof is very easy, and it means that whatever the lattice, whatever the lattice you take in the lattice, you will get all the time the same determinant. So this is very important, and the proof is very easy, and we can find later that there are many applications using the determinant of lattice. Here is another definition about the fundamental domain of corporal PPA of lattice. So the definition is this one. You can get the fundamental domain by using the linear combination of the vectors, the basis B1 to BD, by choosing real numbers between 0 and 1. But you can see that here we are using coefficients real from R, not only from integers. So this is this fundamental domain is important for the lattice, because we can find that the determinant of the lattice is in fact the volume of the fundamental domain. I will show you some pictures about the fundamental domain. For example, here we have a lattice, two vectors, V1 and V2, and for the same lattice we have another basis, U1 and U2, and we know that we can move from this basis to the other one by using the square matrix U, determinant plus or minus 1, and here we can find that the fundamental domain have this value PB, and this fundamental domain have volume PU, and we can find that in fact PB and PU are the same. So here it's easy to see that this this volume is equal to this one, because they have the same vector here and the same height. The height in this equation is similar to this one. So it's very easy to see that these two volumes are similar. Here is another picture to show that we can get the fundamental domain in a lattice, even using a big basis like this. B1 and B2 are very big vectors compared to U1 and U2. Nevertheless, the fundamental domain here and this one have the same volume. So the volume does not depend on the lattice, the basis you use, but only it depends only on the lattice. For example, here you can find that this volume is in fact the same as this one. So we know that lattice has infinitely many bases, and the proof is like this. For example, if we take d equals 2 and u is 3y, 5x, so we need to find some integers x and y such that 3 times x minus 5 times y is equal to 1, and we can see that the determinant of u is exactly 3 times x minus 5 times y. We need this determinant to be 1, so we can find that there are infinitely many solutions, integer solutions to this linear equation, which means that we can find infinitely many matrix U such that the determinant is equal to 1. So we can move from any basis like this to another one by using simply matrix with determinant plus minus 1. So a lattice has infinitely many bases. We can find that some bases are better than others. For example, in this situation, we have a lattice with this basis. So how can we find this vector? So it is not very easy to get this vector using P1 and P2. Because here P1 and P2 are large, and it's not very easy to find the value that will give the linear combination that will give the vector V by using V1 and V2. So we need to move to good basis for the same lattice in order to find how to get the vector V. For example, if we move from the basis V1, V2 to the basis U1, U2, you can easily find the linear combination that gives the vector V, because here in the red one we can find that V is simply U1 plus U2. So it's very easy in this situation than using the vector V1, V1 and the vector V2. So this shows that in a lattice some bases are better than others. So there is a good definition for the fact that the basis is better than another, but in this picture we can see that the red one is better than the blue one. So a good basis is a basis that has some properties. For example, for a good basis we need a short vector, or generally short vectors. Also we need almost orthogonal vectors are orthogonal. In this equation we can see that B1 and B2 are large, and B1 and B2 are not orthogonal. If we compare this to U1 and to U2, the vectors U1 and U2 are short and almost orthogonal. So for lattice reduction, for lattice theory, the basis U1 and U2 is better than B1 and B2. Okay. Now we will give a correct definition for the fact that basis is better than another, but for that we need some definition. The first definition is about inner product of two vectors. So if you have a vector U1, Un, and another vector V1, Vn, then you can get the inner product of U and V by simply computing this sum. Here the sum is from 1 to n of U1 times V1, Ui times Vi, and you can get in this situation the inner product of U and V, and we can get also the Euclidean norm of vector U by using this definition. It's simply the inner product of U by itself, and we take after the square root. So this is the inner product, and this is the Euclidean norm, and we will use these definitions for a using a basis of lattice. So a short vector of lattice is simply a vector which is minimal for the Euclidean distance. So the minimal distance under one of the lattice L is the length of the shortest non-zero vector of the lattice. We say that lambda 1 is simply the distance of V, the minimal distance of the vector V, such that V is the vector of the lattice, and of course V is not equal to 0. So this is the definition of a short vector, and we will see later that short vectors are very hard to find in a lattice. For example, in this picture, this is a lattice with the basis B1 and B2, and the short vector is somewhere in this place, in this circle. Inside the circle, maybe we can find the shortest vector, and here we can see that there are two short vectors. The first one is this one, and the second one is this one. So these vectors are opposite, but we can find that this one is the shortest vector in this situation. So if you have a lattice in a lattice with the basis B1 and B2, in general it's not very easy to find the shortest vector. Here we are in dimension 2, and we can see that in dimension 2 we can find the shortest vector easily. But in some situations, when the dimension is very large, it's very difficult to find the shortest vector. In general, we can get that there are many successive minimum of short vectors. For example, in this picture, we can see that using the vector, the basis B1, B2, we can find the shortest vector. This is the shortest vector, and we can find that there is another short vector. For example, this one is another short vector, but the shortest one is this one, and the next one is this one. So this we give the definition of each minimum. The definition of this is that we need to find which is the shortest vector, which is the second one, and so on. So this is a very hard problem in lattices, because finding the shortest vector is very difficult, and finding the second one is also very difficult, and so on. In dimension 2, in this picture we have dimension 2, it's very easy to find the shortest vector, lambda 1, also lambda 2, but in general it's very difficult to find which is the shortest vector. So this is a famous problem in lattices, the definition of the shortest vector problem, or SVP. So given a basis matrix B or lattice L, we need to compute a non-zero vector B such that B, the norm of B is minimal, that is B is equal to lambda 1 the lattice. So this problem is very difficult in general. We can solve it when the dimension is very low, for example, when the dimension is small, for example, 10 or 20, or even 25, 30. But when the dimension is very large, there is no way to find the shortest vector problem, and this problem is the security reason for some crypto systems. We will say that some crypto systems are based on the hardness of this problem. Nevertheless, there are some results for finding the shortest vector. For example, this theorem of Minkowski it says that when we have lattice L with dimension n, then there exists non-zero vector V in the lattice satisfying this bound. The norm of V is less or equal than square root n times the determinant of n 1 over n. So this is a theorem, but only a theoretical problem. So there is no way to make it practical for determining really to the shortest vector. So the shortest vector exists in every lattice, but it's very hard to find. And this theorem shows that we can in fact every lattice has a very short vector, short such that the norm of the vector is less than this bound. For example, if we take the lattice situation in dimension 2 by this basis B1 and B2, and B1 is like this, and B2 is like this, very quite large numbers, quite large integers, then we can find that the determinant of the lattice is this one, and the shortest non-zero vector is B. We can find that in fact it's 37 B1 minus 31 B2 eliminates 2 and 1. So we can find that this lattice has a short vector, and the shortest vector in this lattice is this one. So we can find that the norm of the vector is around approximately 52. And if we compute Minkowski's bound, we can find that this bound is approximately 93. So we can see here that we have the short vector, and this vector has norm less than the Minkowski's bound. But here we are in dimension 2, and so it's easy to find and to compute in dimension 2, but in dimension larger than 30, for example, it's very difficult to find the shortest vector. There are other problems, hard problems in lattices. For example, the closest vector problem, CVP, is also very difficult to solve in large dimension. When we have lattice with a matrix B and vector B, and vector B is not in the lattice, so we need to compute vector B0. B0 is a vector of the lattice such that the difference between B and B0 is minimal for the Bayesian norm. That means that if we see this picture, we have a lattice. So this is a lattice in dimension 2, and we have basis B1 and B2, and we have vector B, and the vector B is not in the lattice. That means that the vector B is not a black point, but here in this place. So we need to find the closest vector B0 to the vector V. So you can see that here there are four candidates for the vector B0. This is a candidate, this one also this one, and this one, this one. So here we have four candidates for B0, for the closest vector. So this is in dimension 2, and in larger dimension, the number of the candidates will be bigger and bigger, and it's very difficult to find which one from these nearest vectors, which one is the best one, which one is the nearest to the vector. So this is the CVP problem. This CVP problem also is used in cryptography for the security of some crypto systems. And here there are also other hard problems in lattices. For example, we have the shortest vector problem, SVP. Without that, you need to find the shortest vector in the lattice such that the norm of V is lambda 1 and lambda 1 is the norm of the shortest vector in the lattice. Also, the closest vector problem, CVP, when we need to find the vector V U closest to the vector V, or the difference between V and U has minimal distance. Also, there are other problems in lattices. For example, the shortest independent vectors problem is IDP. So this is also a hard problem with lattices, which is used for cryptography. And the next one is the approximate SVP problem, which is quite different from the SVP. Here we need to know if there is a vector such that given gamma bigger than 1 and the basis B for lattice L, we need to compute non-zero vector B such that B, the norm of V is smaller than gamma times lambda 1 L. Gamma 1, lambda 1 is the norm of the shortest vector, or lambda 1 is the minimum of the norm. So we don't need the shortest vector V, but we need another vector which is quite short. Also, another problem is the approximate CVP problem, which is similar than this one, but in this situation we need the closest vector. So we don't need the very closest vector, but we need to find a vector which is close enough to the given vector, the lattice. So these problems are very hard to solve when the dimension is very large, and they are mainly used in cryptography for the security of some crypto system, such as N-true and LV, and also GTH. So there is a way to find the shortest vector when the dimension is very small, and the famous algorithm to doing this is called the LLL algorithm. So I can show you what is the LLL algorithm. So the LLL algorithm can solve some problems in the lattices. Okay. So the algorithm was invented in 1992 by Lenstra, and Bash. So this algorithm is called LLL after authors, and given on the basis B of lattice L, LLL finds the root basis. So the LLL algorithm finds the root basis means that given any basis of lattice, LLL will give you lattice will give you a basis with short vectors and almost orthogonal vectors. And this algorithm is very efficient because it's a polynomial time algorithm, and has various applications. For example, you can find very nice formulas for pi for loop 2, and you can use the LLL algorithm to solve many Diophane time equations. You can solve the SVP problem, CVP problem in log dimensions. But also, the LLL algorithm is used to attack some crypto systems such as RSA, N-true, and cryptanalysis of other crypto systems such as knapsack and GGH. So the LLL algorithm is implemented in many So it's very difficult to use, but the main thing is to find how to use it. So if you have, for example, a Diophantine equation, you can use the LL algorithm, but before that you need to know how to apply it. So it's easy to apply it if you can find the way to go to the way to the using this algorithm. So it's a famous algorithm, it's a powerful algorithm, but you need to transform your program in order to use the LLM algorithm. Before I show you what is the LLM algorithm, we need this theorem from about the Gram-Schmidt optimization method. When you have a vector space V, dimension n, and B1, Bn is a basis of V, and you can find orthogonal basis using B1, Bn by computing B1 star, Bn star, and so on by this equations. B1 star is simply B1, and Bi star is Bi minus this sum, where U, I, and G is the inner product, and the inner product Bi times Bi Bg star divided by this is the norm of Bg star. So we can find that B1 star and Bn star is orthogonal. So this definition, this theorem is by the LLM algorithm for finding a good basis than using the LLM algorithm. So the process of the Gram-Schmidt orthogonalization method is very easy, and we can see here in this picture how we can find B1 star and B2 star by using B1 and B2. So this is B1, the original B1, this is the original B2, and we can find B1 and B2 stars simply by B1 star is B1 and B2 star is simply this one. So there's formulas shows that we can find an orthogonal basis using the basis B1, B2. But can you see that here B1 and B2 is a basis for the lattice? It means that B1 and B2 ends at black points, but here B1, B2 star is not the lattice. So the lattice here, the basis B1 star and B2 star is not the basis for the lattice. It's just the basis for vector space, but not for the lattice. So the B1 star and B2 star can be used to find the vectors of the lattice. When you have basis B1 and B2, Bn, you can find that there is a relation between this basis with the basis with the stars, because we can move from one basis to another by using the matrix like this. When we can see that this is a triangular matrix, and all the numbers here, we can find that these numbers can be computed by using the orthogonal, the Gram-Schmidt orthogonalization method. The situation here for this matrix is that as determinant 1, and we can find that the product of two vectors in this basis, the inner product is always equal to 0, and we can find that also we can find that all the vectors in this equation are orthogonal, but this basis is not the basis for the lattice, just for vector space. Okay, this is the algorithm for Gram-Schmidt implementation. So it's very easy to implement. It's already implemented in almost all softwares. So there is no need to implement it. And it's very easy if you want to see how it works. This algorithm is already implemented in many softwares. And the Gram-Schmidt method can be applied to find other properties of vectors in the lattice. For example, if you have we have matrix with the basis B1 and Bn, then you can get the star by computing the Gram-Schmidt partitionalization method B1 star and Bn star, and you can use this basis to compute the determinant of the lattice. And when you do such a process, you can find that every vector in this basis is shorter than the corresponding vector in this basis. So we can find that Bi star is the norm of Bi star is less than the norm of and also we can find that the determinant of the lattice is in fact the product of all the norm of the vectors of the basis Bi star. When you compute such a product, you can get in this equation exactly the determinant of the lattice, and this is smaller than this product when you compute the product of the norms of Bi, where Bi is the original basis of the lattice. Also, the basis B1, Bn star is used to compute other norms and other properties of lattice equation. For example, in this situation, we can use the basis B1 star, Bn star to find the definition of what is called the LLM reduced basis. This is the definition. You have lattice L and the basis with the basis B1, Bn, and we say that this basis is LLM reduced if there's two conditions are satisfied. The first condition is that the norm U I is less or equal than 1/2. This is the definition through I and G. And the other condition is this one, 3/4 times this norm is less than this norm. So the LLM reduced basis mainly satisfy this one, and this one means that the vectors B1 and Bn are almost orthogonal, and these conditions means that the vectors B1 till Bn are short. So first condition for orthogonality, and the second condition for the norm of the vectors. So a good basis, a good LLM reduced basis is a basis which is almost orthogonal, and where the norms of the vectors are short. So there are many properties. By example, if we see that in this picture, so we have B1 and B2, and also we have B1 star and B2 star, and we can find that B1 and B2 here in this situation is a good basis because B1 and B2 are almost orthogonal, and B1 and B2 also are short. And in this equation, we can find that B1, the basis B1 and B2 is LLM reduced. And there are many properties of LLM reduced basis. When we have B1 and Bn LL reduced basis and B1 star, Bn star, the largely orthogonal associated basis, we can find, for example, that there are many very important properties satisfied by this LL basis. For example, this one, that because of all the norms is less than this bound, and also if the vector of the natural basis has a norm shorter than this bound. Also, we can find this very important property that the first vector of the basis has norm less than this bound, and this bound is used more generally to find the solutions of Layer-Fontaine equation, for example. And also we can find that there are other properties. For example, for each vector in the basis, we can find the upper bound for the norm of this vector. And also very important property of LLM reduced basis. We can find that the first vector V1 has norm less than this bound, and this bound is related to the shortest vector in the lattice. So LLL can give you reduced basis with very, very important properties, for example, orthogonality, shortness of the vectors, but also can solve SVP in low dimension. But when the dimension of the lattice is large, LLL can find the shortest vector, but can find the vector which is smaller than this one. It means that B1 is small, but not the smallest, just small, and sometimes it's sufficient to solve the problem, the Dirac-Fontaine problem for it. So we can compare comparison of the LLL algorithm with this bound. This is the bound with the LLL algorithm, and this is the theoretical bound with the Mantoux theorem. And we can find that in fact this is very small than this one. So this is square root of n is smaller than this. This is 2 to the n minus 1 over 4 is larger than generally than square root. So the other thing is that the LLL algorithm is an efficient algorithm because its complexity is polynomial, and this is bound for the number of operations of the LLL algorithm. So it's a very powerful algorithm and can solve many problems and Dirac-Fontaine equations and also cryptography. So this is a numerical example for the LLL algorithm. So we have lattice L with basis U1 and U2. You can see that U1 and U2 are large, and the determinant impact of the lattice, you find that it's very small, only element, and the LLL algorithm, if you apply it to U1 and U2, you can find the new basis B1 and B2, such that B1, the norm B1 is less than this bound. That means that the norm B1 is very small than the norm of U1 or the norm of U2. So the LLL algorithm outputs basis B1, B2 with B1. This is B1 and this is B2, and you can find that the smallest norm is B1, and it's almost approximately 3.6, and the theoretical result is 3.9. So the LLM algorithm is very efficient. For for example, for solving some problems like this. So here we have quadratic expression with three variables, x1, x2, and x3, and we have f the three variables like this. This is squared here, and this one is squared here, and the next one is squared here. So we need the minimal. We want the minimal value of this function. How to find x1, x2, and x3 such that f x1, x2, x3 is minimal. So it's very easy to solve, but we can apply the algorithm to solve this problem. So the difficult way is to transform this problem into basis and to vectors, so that we can apply the LLM algorithm. So we can see, in fact, that this function can be transformed like this. But this is the first one. This is the first term. This one, and the next one is the second term. The last one is the last term. So this is a vector v, and we can transform the vector v like this. So we can write that v is x1 times u1 plus x2 times u2, 3 times u3, and this is u1, this is u2, and this is u3. So we can find now using u1, u2, and u3. You can find the basis b, and this basis can be the matrix of lattice L, and we can reduce the lattice L using the LLM algorithm in order to find a short cut. So when we apply the LLM algorithm to the basis with vectors u1, u2, u3, you can find that the LLM reduced lattice is very short. You can find b1 like this, the shortest vector is b1, the next one is b2 like this, and the next one is b3. So after that, we can find that this equation, we can get each one x2, x3 using by solving this system of equation, because we know that this one, this first term, will be minus 23, the next one will be 11, and the last one will be 12. So we can solve this system to find x1, x2, x3, and we can get that x1, x2, x3 are very large numbers. Nevertheless, when we apply the function f with these very large numbers, we can find that we can get a very small result here, 7, 9, and 4, and this is the minimum value of this equation. So it is not very easy to solve it directly, but by applying the LLM algorithm, we can transform the problem into basis vectors, and apply the LLM algorithm and find that the minimal value of this function is this number. So the LLM algorithm is not very hard to implement, but it's already implemented in most softwares. So this is we can get this algorithm in one slide, but I'm not going to explain more deeply, because the LLM algorithm is easy to implement, and we don't need to implement it because in most softwares it's already done. So there are many applications of the LLM algorithm, mainly to RSA. RSA was invented in 1978 by Abderrahmane. It is used widely used in many industrial applications. For example, RSA is used for encryption, signature, implemented in all web servers and browsers. It's used for securing commerce and emails for the authenticity and element events. It's used for most commercial security products. And the security of RSA is based on two hard problems. The first one is the integer factorization problem, and the second one is called the RSA problem or the heat modeling root. So RSA is famous because it's used mainly everyone when the security is problem, and LLL can be used to attack the RSA algorithm, RSA scheme. For example, we can use the LLL algorithm inside the Cooper-Smith method. Cooper-Smith method is a method to solve mainly Dirichlet equations. For example, we can apply the LLL algorithm to solve this equation where f is a polynomial and with the n variables and each one is n, and we need to compute the smallest solutions of this polynomial equation modulo n. So the principles of Cooper-Smith method are like this. F is a polynomial with small roots. We can use F to build other polynomials sharing the same root. We can use the new polynomials to build the lattice L with the basis B. And we can apply the LLL algorithm to reduce the basis B. And we can also, after that, we can reduce the basis. And after reducing the basis, we can solve some systems, for example, by using resultant techniques or nominal basis techniques. So these are the principles of Cooper-Smith method, and Cooper-Smith method is very important data, for example, RSA, because we can find some weak instances in RSA. For example, we can use Cooper-Smith method to solve this equation. So this is the key equation in RSA, when RSA is used with two many parameters, mainly the parameter E times D minus this product, and this key equation can be attacked by using Cooper-Smith method. First, we can transform this equation to this one, and this one can be transformed into polynomial equation. So we have this equation with two variables x, y, and we can then apply Cooper-Smith method to solve this equation. And if we can find the value of k and the value of p minus q minus 1, then we can solve this equation and we can get the value of d. So in RSA, e is the public parameter, and E is the public parameter and D is the private parameter. And if we can solve this equation, then we can get the value of D and break the system. So Cooper-Smith method consists of transforming this equation to polynomial 1 and to a lattice, and reduce the lattice and solve some system. And finally, you can find the value of all the parameters of this equation. So this is the attacker of Bonnie and Durfee to attack the RSA system, and we can find some results about which one. Okay. Yes. Finally, when you use cooperative method, you can find that RSA is insecure if the circuit parameter is small, d is smaller than n to the delta, and delta is this situation. That means that you can't use RSA with small private parameter d. So if you want to use RSA, you have to use a large parameter, private parameter d. So this is the application of the cooperative method to attack the RSA by using the algorithm. Also, there are other crypto systems that the security are based on lattice problems. For example, intro. They can show some slides about intro. So intro was invented by Hofstein, Pfeffer, and Silverman in 1996. The security is based on SVP. SVP is the shortest vector problem, and there have been many versions of intro between 1996 and 2001 because for security reasons, and mainly the security of intro is mainly based on the SVP problem, and the SVP problem is a hard problem in practices. How much?
3 times. What do you think?
Okay. 2 minutes? 5 minutes? 10 minutes?
3 minutes.
Okay. Yes, okay. The arithmetic in intro is very different from RSA, for example, because in intro we work with polynomials, modular polynomials. For example, if you have a polynomial f and polynomial g, you can find the sum of f and g. This is very easy. Just add the f0 and g0 and so on. But the product is different because the product of two polynomials, you will need to use this congruence because it's a convolution product. So the arithmetic is based on polynomials, and okay, the key generation is very easy. You can generate two polynomials f and g. You compute the inverse of some of f, the inverse of f modulo t, the q, and the public key will be this product, and this product will be public. So we can try to adapt intro using this equation. But you can see that in this equation, the two polynomials f, q, and g are private. So there is no way to find these polynomials. Nevertheless, we can transform this to lattice problem and try to use LLL algorithm to apply the LLL algorithm to solve this new problem, and we can find f and g when f and g are small. So if f and g are small, we can apply the LLL algorithm and solve this equation, and also we can find the value of f and g and bring totally into system. Now there are many other applications of the LLL algorithm, and that is the lattices. For example, we can apply an element to RSA, to intro, to LV, to GGH, to knapsack problems, and so on. So I'm sorry, I have no time to finish my talk. I just need to. Okay, conclude. Okay, lattice-based cryptography. Lattices are used mainly in cryptography. Lattices are used to build cryptographic schemes such as GGH, intro, and LV. Lattices can be used to build fully homomorphic encryption schemes, digital signatures, non-digit encryption, ABE functions. There are many hard problems in lattices that you can use for cryptography, for example. Also, lattices can give fast interpretation, and for the moment, lattice problems are resistant to quantum computers, also to RSA. So the future is certainly for cryptography. The future is for cryptography based on lattices, because if someone can use quantum computers, so he can solve many problems in cryptography, mainly RSA, discrete codec problem, and so on. So thank you very much. Terima kasih.